The discovery and application of radio astronomy helped to define our own vast sun cluster, but hasn't diminished our amazement.
Our Milky Way galaxy is a huge disc-shaped system of, say, 100 or maybe even 200 billion star years from one side to the other. Our sun with its planets is located about 2/3 of the way out from the center, and the sun, like all the stars in the galaxy, travels about the center in an orbit, and it takes the sun 200 million years to complete one circuit around. The sun's probably done that, or maybe 25 times since it was first formed. Well, we have an idea, at least a general idea, of what our galaxy is like, how big it is, its shape, and so on. But it's very difficult for us to get that picture, to put it together, because we're inside the galaxy, and we don't get to look at it from above or below or on the edge, at least not from the outside. It's a lot like that classic sort of a detective tale, the locked room mystery, in which a crime is committed, seemingly impossibly, inside a locked room. The criminal has either gotten in or gotten out in some unimaginable way, and yet the detective, with his clues, is able to find out some ingenious solution how that happened. Well, the detective has an advantage. He's able to go inside the room and outside it and around it in his search for clues. But in the conundrum of our galaxy, we're forced to stay locked in that room. In fact, we're not even allowed to leave our chairs. We can look out the window, and we do see other galaxies out beyond our own. And some of them, at least, are spiral galaxies. And in ordinary visible light, at least around us, we see hints that our own galaxy is also a spiral. But we really can't put the whole picture together from that information. It's still a lot like being in a marching band, on a football field at halftime, on a field, in fact, that is smothered in fog. We can here and there around us, but we can't put the whole pattern together because of the obscuring fog. However, we do have an answer. Radio light can penetrate that fog, the dust of our galaxy that obscures our vision. And in fact, radio light shows us that our galaxy does have a spiral shape. And so radio astronomy is our escape from the locked room.
Once astronomers had determined the general characteristics of the Milky Way, they began searching in our own galaxy for evidence of the spiral arms that had been seen in other galaxies, such as Andromeda. In the 1920s, both Lindblad and Oort analyzed the stellar motions in the Milky Way and determined that our galaxy was rotating. Later studies showed that our neighboring galaxies also exhibited this rotating pattern. This rotation provided at least a theoretical framework for the distribution of the stars in the spiral arms. However, the nature of that rotation was still to be explained.
We speak of the Milky Way galaxy as a wheel or a disk, but it's not really a solid disk. Of course, it's composed of billions of individual stars and clouds of gas and dust as well. And they're all moving in their own individual orbits about the center, dancing in concert with the laws of gravity. And of course, the final result is an amazingly complex collection of motions. This final result is not rotation like a solid wheel's rotation. It's actually called differential rotation. If we were to look at the galaxy's movement in detail, we'd see at least the centermost part of it did behave like a solid wheel. But as you go farther, it's like what happens in the solar system. The innermost planets travel at high speed, the outermost planets are slower and slower still. And so the stars farther out from the center travel more slowly than those in toward the center. And we see then this differential rotation. Well, we can map it out if we make careful observations of the stars. And it's very important that we do that as well. An understanding of the details of differential rotation can be applied to our observations with radio telescopes, and that's what permits us to map out the spiral structure in our galaxy.
Within our rotating galaxy, astronomers are hunting for spiral arms optically by studying, for example, the hot blue stars in the H2 regions. In other galaxies, these areas of dust and gas collect in the arms. Using a photometer, the astronomer can record on a chart the brightness of the stars he observes. These charts are then analyzed and interpreted, a job that takes more time than the actual observations. The information on stellar brightness can then be transferred to a plot that reflects the location of the hot H2 region stars. The optical maps provide a basic indication of the location of the nearest spiral arms. However, the optical mapping technique has the very dust and gas the astronomer is studying.
First, you're looking the long way through the Milky Way. This is a big, flat, pancake-shaped disk. And there's a lot of dust in there and a lot of gas. And of course, when you're looking with light, it doesn't make it through on a dust through all the dust. And the light rays just can't penetrate it. As we all know, on a windy day out in the desert, you don't see very far.
Consequently, only those portions of spiral arms within a few thousand light years of us are revealed by optical mapping. Still in all, by looking for certain markers of the spiral arms, such as the very young and luminous stars, certain star clusters, and clouds of interstellar gas, we can observe, actually, pieces of 3 spiral arms visually without the need of the radio astronomy.
However, an accurate picture of the total extent of our spiral arms required the development of radio astronomy. Radio light is able to pass through the clouds of dust and gas that obscure visible light. The history of radio astronomy began with the discovery of radio light.
Heinrich Hertz discovered radio waves in 1887, and not long after that, actually by 1890, Thomas Edison was proposing to try to detect radio waves from the sun. In fact, he thought he would do this with a big field of iron ore by stringing telephone wires around it to be his radio telescope. And over in England, just a few years after that, Sir Oliver Lodge also tried to detect radio. Sir Lodge were successful.
The actual first detection of natural radio emission from beyond the Earth was in 1932 by an engineer named Carl Jansky. Jansky was with the Bell Telephone Labs, and he was given the task of tracing down some interference that occurred regularly. And his discovery was that it happened every time the center of the Milky Way passed overhead, over the antennas, which at that time were located in New Jersey. So he was able to verify that there was a radio emission within our own Milky Way, which peaked up at the center of the Milky Way and made some natural limit to how much energy you could propagate via telephones. So then there was a long pause. The odd thing is no one picked up on that discovery, and Jansky's whole research lasted about 1.5 years at the Bell Labs. And there was one lone amateur named Grote Raber who found this very interesting, built himself a parabola in his backyard in a suburb of Chicago, and began studying the skies at night. Now here's a guy who carried on a full-time job all day during the week, went home at night and stayed up all night and studied the heavens, the only guy in the world doing it, with a telescope of his own creation. And surprisingly, that telescope resembles very much today's modern-day equivalent. So the guy named Raber deserves a lot of credit for keeping his influence, and he made many of the early discoveries.
He got a little bit of electrical interference from passing automobiles with their ignitions and trolleys, which also ran on a local dentist drill. But he still managed to make some of the first observations of professional nature in radio astronomy. And his work was carried further by J.S. Hay in England. During World War II, Hay was involved with investigations of enemy radar jamming. But after that, he also got involved with radio astronomy. And he, among his many contributions, mapped the radio sky. Well, it's this kind of work that led us to be able to sketch out the details of our galaxy and realize it has the spiral structure we see.
The critical breakthrough in radio astronomy came with the discovery of the 21-centimeter line, a radio wavelength emitted by neutral hydrogen. This 21-centimeter emission was predicted in the laboratory in 1944 by H.C. van der Hulst, a Dutch astronomer, during studies of hydrogen gas.
The most important kind of gas in the interstellar medium is hydrogen. Now, these hydrogen atoms are far apart, but every now and then they collide. And when they do so, sometimes the nucleus of one of the atoms is flipped upside down with respect to the electron's orbit. Now, the hydrogen atom doesn't stay that way very long. After a few million years, it'll jump back again the way it was. And in doing so, it emits a photon, but not a photon of visible light, but of radio waves. It was predicted by van der Hulst that this kind of radiation should be observed from the hydrogen gas in interstellar space. And it was observed when radio telescopes were made with enough sensitivity to observe it in the 1950s. Now, the important radiation is it is a discrete spectral line. Those waves come at that unique frequency corresponding to a wavelength of 21.11 centimeters, as I recall. That means that this radiation shall show a Doppler shift if the source of light is moving away from us or toward us. That is to say, the radio wave should show a shift, just as visible light shows a Doppler shift. Now, the galaxy is rotating like a wheel. The interstellar matter is mostly concentrated in the spiral arms of the galaxy that wind out from the nucleus like the arms of a pinwheel. Now, from our vantage point, we are moving around the center of the galaxy. If we look in various directions, different parts of different spiral arms that might encounter our line of sight are going to be moving at different speeds in our line of sight, aren't they? And therefore will show different Doppler shifts. So all we have to do, once we've established the pattern of rotation in the galaxy, is measure the Doppler shift of the 21-centimeter radiation coming to us from some distant spiral arm to know how far away that spiral arm has to be in the galaxy. So by many observations looking in the plane of the galaxy, we can actually map out where the spiral arms have to be to account for their motions toward or away from us as a consequence of their and our motion around the center of the galaxy.
The 21-centimeter line from neutral hydrogen that was predicted by van der Hulst was finally detected by Ewan and Purcell at Harvard in 1951 and is now being studied by instruments such as the newer Harvard, whose reflector works much the same way as the mirror in an optical telescope. Instead of a highly polished surface, however, the radio reflector is covered with half-inch open mesh. The radio waves are reflected to a point of focus where the feed horn builds up the signal strength and sends it down to the receivers in the control room. The receiver must be tuned to the wavelength of the region to be studied, as well as to the velocity and position. Most radio telescopes can be steered and pointed at any position in the sky. This telescope has both an east-west movement and a north-south movement. Usually, the instrument is not pointed directly at the particular area to be observed. Instead, it is aimed slightly to the west. The telescope is stopped, and then the rotation of the Earth sweeps the antenna past the desired area. Radio telescopes record their findings from the amplified signal on charts, the pen in constant motion. When the neutral hydrogen is detected, the pen moves farther to the left. The greater the sweep of the pen, the greater the amount of hydrogen measured. Because of the motions of these clouds of gas, a spread of wavelengths is measured. Each of the 6 lines represents a slightly different wavelength or different velocity. The fluctuations in each line indicate the intensity of the signal. These charts can then be translated into radio maps. From the edge, one region of the Milky Way would look like this, with the brightest spots representing the most intense sources of radio signals. From the top, those radio signals give us this view of the Milky Way, clearly showing that we do have the spiral arms observed in other galaxies. The break in the radio map is caused by the emissions from the nucleus of our galaxy, which overpowers the radio light from the far side. The galactic center, the nucleus of the Milky Way, was one of the first radio sources discovered. It was identified in the 1930s by Jansky as Sagittarius A. But much additional information about the nucleus now comes from infrared studies.
The far infrared radiation from the galactic center, equivalent about 700 million suns, is remarkable in that it indicates most of the energy produced by stars, by the nuclear processes in stars, radiated visibly from their surface, ends up in the far infrared. The mechanism for that, which appears now to be rather well established, is that this radiation is absorbed by the very tenuous but enormously extensive dust clouds in the center of our galaxy and throughout the galaxy, heating these clouds slightly to temperatures still below those of liquid air, and re-radiating in the far infrared. Since those early discoveries, we and other observers have found that in a good deal of the galaxy, these dust clouds reveal themselves by their far infrared emission. And in addition, rather hotter dust appears around a great number of stars.
These very young stars are often grouped together in open star clusters. In the open star clusters are masses of dust and gas, H2 regions, that are rich in hydrogen and are the birthplace for new stars.
But today, the only place we're going to find star formation occurring is in those regions of the galaxy where there's interstellar matter, and that's the spiral arms. So you find the young stars, which have recently formed, among some old ones too, in the spiral arms, where you also find stellar material.
When a young star becomes very hot and produce a great deal of ultraviolet radiation, it then begins to ionize the hydrogen gas, which has been left in the region around the star. This process, the ultraviolet, is absorbed and the hydrogen gas left ionized, and so attenuating the radiation from the star. But as the nearby area becomes totally ionized, it becomes transparent, and then the gas further out is ionized. This process continues, so as time passes, a larger and larger region around the star becomes totally ionized hydrogen gas. This is what we call an H2 region. In one of the recent observations made in the C-141, a rather intense region of infrared from a dust cloud at some small distance from the new star, the H2 region, has been observed where the dust cloud is clearly displaced from the new star, and where the greatest amount of heating of that dust cloud occurs right at the edge of the ionization, producing the ionization region, which we call the ionization front. And what appears to be happening there is that as that ionization region has moved out through the hydrogen gas, it has come upon the dust cloud, which now begins to absorb the ultraviolet and consumes so much of it that further ionization cannot occur of the gas beyond. So the dust stalls the expanding ionization region, and hence we have this ionization front pushed up against a dust cloud. There's some other examples of this and some speculation that perhaps the pressure of this ionization region up against a cloud of dust and molecules causes a compression of that cloud and triggers a collapse, which then could provide additional star formation. So the interesting aspect of this particular observation and mechanism is that it could be a means by which stars are sequentially triggered. One star providing a mechanism to increase the likelihood of other stars forming in the area.
Radio telescopes have shown us the spiral arms of our own galaxy by detecting and recording the 21-centimeter radiation of neutral hydrogen. The cold neutral hydrogen and the hot glowing hydrogen of H2 regions are the areas of dust and gas in the spiral arms that give birth to new stars. But the formation and structure of the arms, their stable spiral pattern, continues to interest astronomers.
The formation of the spiral arms is an extraordinarily difficult subject. The favorite idea is due to C.C. Lynn. And Lynn's hypothesis is that gravitation is what's at work to make the spiral arms. But if we take account of the gravitational attractions of the spiral arm material for itself, as well as the other stars in between the spiral arms and in the spiral arms and the galaxy as a whole, he's been able to account for kind of a stable structure of spiral arms, that is to say, a stable spiral pattern. The spiral arms do represent regions of the galaxy where the density of matter is a little greater than in the intra-arm regions. And apparently the whole spiral pattern maintains that pattern while the whole galaxy turns, rather than the arms winding up tighter and tighter as one might expect. And this pattern is maintained because of the peculiar way the stars move around the galaxy. The stars and other matter slow down slightly in encountering the denser spiral arms because of the gravitational effects there. And then they speed up again in the intra-arm regions. So the spiral structure is kind of a density wave in the plane of the galaxy.
We've examined the nucleus of our Milky Way and the spiral arms that extend out from it. But our galaxy also has a faint halo of random stars and globular clusters.
The halo of a galaxy is the most spread out part. Actually, a halo comes from a Greek word which described an ox going around tied to a stake treading out corn. The whole idea is something which is, although it may be centrally concentrated, is also very spread out rather than in a disk or in a more compact form. Our interest in the halo comes about because we think the halo consists of the oldest stars in our galaxy, and ones that are chemically somewhat distinct from most of the stars, like the Sun, we're more familiar with. The halo is dynamically and kinematically different from the other stars in the galaxy. It's more spread out, and we think it represents the earliest stars that were formed when the galaxy was formed from presumably primeval matter.
Probably the most plausible idea for the formation of our galaxy is that it formed very much the way the solar system formed within our galaxy, but of course much longer ago. The solar system condensed from a cloud of interstellar gas about 4.6 billion years ago. The galaxy must have condensed in a similar way from pre-galactic material, presumably gas made up mostly of hydrogen and helium, but some 13, maybe 15 billion years ago. The galaxy is at least 2 or 3 times older than the solar system. Presumably there was some rotation of that pre-galaxy material, and as it slowly pulled together of its own gravitation, it spun faster and faster to conserve its angular momentum, like the ice skater who pulls her arms in, and as a consequence flattened into the more or less disk shape that we see the galaxy today. And in this flattened disk of rotating gas, subcondensations became the stars and star clusters. Some of the material was left over and remained as interstellar gas. But subsequent to the formation of the galaxy, the interstellar matter has continually, here and there, been forming into stars. So whereas most star formation probably occurred in a burst early on when the galaxy first formed, still a sprinkling of stars is continuously forming. When the sun formed 4.6 thousand million years ago, it formed of different material from that which the galaxy formed from much earlier, because the galaxy was probably formed mostly from hydrogen and helium. But by the time the sun formed, much of that material had been cycled through stars, been synthesized into heavier elements by the nuclear reactions that kept those early generation stars shining, so that when some of those stars spewed some of their matter back into the interstellar medium, it contaminated the original gas and dust, so that new stars like the sun that formed contained some of those heavy elements, such as those that make up our bodies and the Earth and the other planets.
The Milky Way, Milton's broad and ample road of stars, has meant different things to different people. The California Indians thought of it as a pathway of human souls making their departure from this earth. And our modern conception may not be so poetic, but it's no less interesting. We follow that path of the Milky Way on a quest for understanding, and we've widened our eyes to see in radio light and the spiral pattern of our galaxy that it reveals. And these are just hints of surprises that are to come in infrared, gamma rays, and X-rays. There's a galaxy of discoveries ahead of us.